Hey everybody, thanks for coming out today. My name is David Scott and I'm a machine learning engineer on the Caper team within Instacart. And today I want to share with you guys one of the things we're doing within Caper right now, and this is specifically something that we were building on Ray, and it's basically scaling computer vision models with Ray. And so today I'm going to walk through first table of contents right now. So first I'm going to give you a little bit of an introduction about Instacart and Caper. Afterwards, we'll chat a bit about the computer vision and AI teams within Caper. As well, too, is scaling our computer vision workloads. And finally, we'll talk a little bit about the results, evaluation, and the conclusion. So first is Caper. What is Caper within Instacart? So Caper was originally a startup that went through YC program quite a few years ago, and Instacart acquired Caper at the end of 2021. So some of the original versions of the Caper cart that you might see, and this is an actual hardware product that you can utilize in grocery stores, is basically like an intelligent barcode scanner with an UI that you see on the right-hand side. Maybe similar to an Amazon Go cart if you've seen an Amazon Go cart before. And then now we're moving on to some of our future generations of that are actually utilizing AI at scale in order to scan products in real time. So what does a seamless shopping experience look like for our customers? Essentially, like with the cart right now, as you can see probably from the initial viewing, is we have quite a few sensors integrated into the cart. So you can probably see on the top of the cart right there is we actually have cameras that are embedded within the cart, and as well things like a barcode scanner too. One thing that's quite interesting as well is actually the bottom of the cart has a scale on it. So as you do things such as like adding produce products, for example, is that we can actually weigh the produce products in real time as you're adding them into the cart. And then finally, too, one thing that we're working on is actually real embedding information of where the cart is located in the store. Because one thing that we'd like to do in the future is basically give our users like intelligent ability to like give advertisements to our users or like coupons or discounts in real time. So we're also looking at the live location of where the carts are in store too. And then next is basically talking about like how is computer vision and AI actually like integrated into our products. So the first thing is the hardware itself. And then the next thing that we have to do with that is basically the computer vision portion of it, right? So within the computer vision portion is one of the things that we're looking at is such as like object detection. So object detection, for example, if you're not familiar with it, is basically you have an item within an image, and essentially you want to determine where is the item located within that image. And finally, how are we doing this at scale and in real time? Because as we're adding items into the cart is we don't want any lag or feedback for our users. So we train with things like Python and kind of more simple training frameworks, but actually at scale when we're deploying our systems is we're utilizing things like C++ to basically give us the best inference possible in real time. And so in order to unlock a magical shopping experience for our users is we essentially enable seamless AI that can detect products and recognize them in less than 0.5 seconds. So let me just try to play a quick example for you guys of, say, how a user would utilize our product in real time. And I'll play it back over and talk a little bit about the video. So, oh, my apologies, let's go back. So essentially with the user adding the product into the cart is so you can kind of see, sorry about that, you can kind of see how the object detection problem would work here is that from the video is we essentially have, let me just exit out of this more videos, is we have the cameras in the back and we have cameras in the front of the cart, and as the product is coming into the cart is essentially that object recognition portion of the pipeline starts. So we are essentially, say, like the user's adding the product in, and the views that we have from the cameras is immediately already detecting that object coming into the cart at that time, and that's basically where our entire machine learning pipeline starts at that particular instance. And so I'll just kind of quickly talk about the computer vision portion, and then as well too afterwards start getting into kind of the meat of this presentation, which is basically the training and whatnot. So for the computer vision, like I was mentioning, is the basic problem is object detection. So we're trying to identify that problem or product within the frame. Second, pretty much object detection is like one of the most important portions of any computer vision pipeline, because if you can't get object detection to work properly, every other part of your machine learning pipeline down the line essentially is going to suffer because you're not getting the object detection right at the first part of the problem. And then how are the computer vision models trained? So basically we train with labeled images. So we'll do some types of like data collection, and then we have to do data annotation and understand like on the bounding box of where that product is. And then as well too is make this robust for like real world conditions where every store is going to be quite different from one another, is we have to augment our images with say like different noises or different variations in order to get them to basically like have more variability and more understanding across different stores. And so let's get into more kind of like our traditional training framework of what we were doing beforehand, and then we'll start moving more into say some of the comparison between Ray and Kubeflow. So for beforehand, how this would look like for us is basically utilizing like Docker containers across different servers in order to make sure we have like reproducible environments. If any of our GPUs were different between the different types of servers that we have, we can easily basically work horizontally with those and get them to integrate with each other without any issues. Secondly was actually the use of GPUs. As you can imagine, basically, in like day and age right now with LLMs and computer vision models, is if you want to train really large models on a lot of data, is CPU is essentially like very unable to basically work up that scale and get it to train quickly. So for us, it's essentially critical that we're utilizing GPUs in order to train our system. And then third is the distributed training component, is that we basically have to, like in our traditional case of not using cloud, is like we would have to essentially get our servers to connect with each other's on our local server setup to essentially get like our models to scale and train well in that instance. Otherwise, we're not going to be able to train things in a very quick timeline. And so looking a little bit back at, say, like what our kind of like previous generation like training system would look like is something like this. So an engineer would basically kick off a training job, and essentially like we would have a server set up in like one of our office locations across the world. And basically like the engineer would already move, say, like these Docker containers onto that particular server or sets of servers, and then we'd have something like a network file system like NFS set up in order to get this to all connect properly. And then essentially the training process would kick off. So the training process would look a little bit like this, is basically we fragment a model across the different servers. We'll also fragment like shards of our data across those particular servers too. Through the training process is we'll have some type of like gradient differentiation on each server that we're working with, and then at the end of a particular step is we'll basically go and average our gradients from that particular epoch, and then once the training is done, we'll save the model somewhere locally. And I'm sure as many people know, is like doing this by yourself is difficult and you will run into problems. So this was one of the things like we wanted to kind of think about like as we were looking to basically like maybe go to more of like a cloud-based framework, for example. So for us, one of the things is we want to have scalable distributed training for our cloud-based system. And kind of the reason for that is we just wanted to have more ability to basically, if we easily needed to bring instances up and put instances down, just have that kind of at the tip of our fingers in order to do. So like some of the things that we looked at for this was Kubeflow or Ray to basically speed up our training jobs. Second was optimizing our training speed. So one thing I'll talk a little bit about is for computer vision models in particular, especially if you're working with very small image sizes, is you're basically going to be opening in the ranges of anywhere from tens of thousands to hundreds of thousands or millions of images quickly and basically writing and reading on them. So by frequent opening and loading of numerous small image files is you run into a lot of I/O bottlenecks. So how this could actually happen afterwards is your GPU utilization is low because you're wasting all your time basically processing your data in order to feed it into your GPUs. So, and as well too, obviously using additional GPUs for training is nice. So if we don't have to use our local GPUs and we can use cloud-based GPUs, that would help us too. And then finally too is also the ease of use. Onboarding for us is interesting because not everybody in the team has like super strong expertise in say like machine learning infrastructure and like basically running systems like on the cloud. So we wanted to just give like the other engineers on our team like a very like simple way to basically get them like into like a cloud-based like training environment and allow them to like scale their systems more easily. And obviously, too, minimizing cost is great. So if we can use spot instances as possible, that was obviously of interest to us. So kind of going back into the training requirements like I was talking about in the last slide is the high throughput was essentially critical for us just given the small size of our image files. So like actually one of the images here is an example image from one of our training setups beforehand. And you can think like we'll have like tens of thousands, hundreds of thousands, millions of images just like this that we're basically opening and closing all the time during our training setup. 2 is the training speed and the scalability. So like I was mentioning, the GPU utilization is critical in order to basically like maximize your training speed and as well get the most out of your training setup. And as well dynamic scaling. So basically like depending on how we were going to train our job, if we needed more GPU instances, we wanted to be able to dynamically scale our GPU instances. If we needed more RAM-based instances, we wanted to be able to dynamically scale like our RAM-based instances. And finally is the operational efficiency. So essentially as, I think a lot of teams right now are trying to do more with less. So like we wanted to have like easy maintenance, for example. We didn't want like our engineers to have to go through and do a lot of debugging like in the cloud in order to get the system to work. And finally is the integration flexibility. So basically like being able to easily integrate with our existing tools. So things like Docker containers, if engineers want to write a script in Python, things like that, just giving them the easy ability in order to basically like integrate with this tooling. And so what did this look like for our experimental setup and how were we basically evaluating some of these like training setups? So for us is we were training a model called Delft-Keras, which basically is more of like an object recognition model. So that's why like beforehand I showed you the bag of the peanuts because we're actually like recognizing like lots of images at scale in real time. And we utilize like AWS for our cloud-based partner in this. I mean, you can kind of utilize like whoever you like, but we utilize AWS. And we basically were comparing Ray and Kubeflow in this particular experiment and seeing how well they were basically going to work against one another for our criterias. So for our method of comparison is we basically set up like a different, or had quite a few things that we were looking at. So I'll start with 3 and I'll move over to the other 3 afterwards. So for the first one was basically the time required for setup, understanding of the tool, and as well the configuration of the tool. Second was how well each system responds to scalability and performance in real time. Third would be the cost analysis. So this would include things for us such as like storage, because you have to keep your data somewhere, and as well instance pricing, and just any additional overheads that you have with that particular system. So finally would be the performance metrics around the training time, the GPU utilization, and as well our I/O throughput. Fifth was kind of the integration and our compatibility with existing systems and basically like onboarding our engineers into that system. And then 6 was basically reliability and fault tolerance because we don't want to lose any training jobs while they're being kicked off just because it's going to be costly and basically slow down our engineering teams. So what did this look like for us kind of like as a proposed solution? So depending on the like type of framework that you utilize, for example, like if it was going to be Ray for us is we would basically like kick off our training jobs like utilizing like a traditional like training script, for example. Versus Kubeflow is we were basically utilizing like YAML files to basically do all the initial like work at the beginning. And pretty much how this would work for us is we would have an EKS cluster, and EKS is Elastic Kubernetes Service on AWS for anybody that's not familiar. But basically, we would essentially kick off a training job, send it into our EKS cluster, have a head node that would basically start kicking off the training job to any of the worker nodes. From our data store, we would essentially like shard portions of our data in order for it to basically like go into our worker nodes, which would be the GPUs. And then finally is we would have some type of like monitoring or type of services like that during our training job that would be able to like look into it. So we'd look at things such as like Grafana or like MLflow for like saving some of our like particular training pieces, and as well Datadog too for like monitoring any of the log lines and like any issues during our jobs that we might run into. And then one other portion of this that was quite interesting for us as well is actually like being able to optimize our data loader within Ray data. So for anybody that's not super familiar with Ray data, and I'll just bring up all the pieces right now. Anybody that's not super familiar with Ray data is it essentially allows you to actually like kind of recreate some of your data pre-processing steps and allow it to kind of like scale within like Ray Train or like any of the other Ray services. So some of the things that we did is basically like worked on parallelization because we really wanted to actually utilize like RAM-based instances to basically pre-process like all of our data and then quickly feed it into our GPU instances to basically like saturate our GPUs as quickly and easily as possible. As well too is like Ray Data does offer built-in support for streaming execution. So we did notice like that was quite beneficial for kind of like large scale training setups because like the more GPUs that you have, like you want to be able to like easily stream data in. And finally too is another nice thing that we noticed with Ray Data is you can actually like implement your own like user-defined functions like UDFs inside Ray Data. So if you have any like kind of like pre-processing criteria for like the type of like machine learning pipelines that you're working with is you can actually kind of like create those within Ray Data to work effectively. And so like an example of like our particular case of like how this looked like is like in terms of like rebuilding our data loader is we have some user-defined functions which would be like parse file names, resize and pad images, adding keys, and then stack images along channel axes. And we can actually do like mapping, sorting, and group bys like quite effectively with that, just using the built-in API that Ray Data has, which is just read images. And then within the train loop config is it might just be particular things such as like your image size or any other types of config information that you need for your training job. And then going into the results and evaluation. So for Kubeflow is one of the things we wanted to look at was the time required to utilize the tool. For Kubeflow, what we found at the beginning is basically, it's kind of similar in Ray is that you have to manually set up your Elastic Kubernetes clusters and your autoscalers. But actually like getting everything to get set up out of the box because there's so many like moving components it did require like several hours to basically like set it up and get it to work like well for our team. Another thing is too is that because we took the path of basically like allowing our engineers to like create jobs from YAML files is we had to write a lot of documentation for our team for like, you know, our engineers to basically understand, okay, if you're going to set up a YAML-based training job, these are all the steps you need to do. You need to bring your Docker image onto Elastic Container Registry, ECR within AWS. So there was a little bit more headway needed that we found. And Ray, for example, is because all of our engineers are super familiar with Python is that we're, you know, all we say is all you have to do is like import your TensorFlow trainer and then maybe make a couple of small changes like in your training setup, like recreate your training loop. And basically you can start kicking off your job and also allocate some particular pieces like the number of workers that you have or like the use of GPU and whatnot. And yeah, we found like having the integration on Ray there was quite effective for our team. So in terms of performance metrics, say between both Ray and Kubeflow is like in terms of scalability, we found that like each system does leverage autoscaling in cloud instances. So the scalability we could say between like Ray and Kubeflow is quite similar actually. Similar with like reliability and fault tolerance, like both systems do have some ability for like fault tolerance and reliability. So like we didn't really find like a huge difference between like Ray and Kubeflow for either of those. And one of the things I'll chat a little bit more about afterwards, but we did actually find we had some cost analysis for Ray, mainly because we were actually able to store our data in like S3 instead of like elastic file storage like EFS within AWS. And S3 is actually a lot cheaper than EFS for storing data. So we actually noticed like quite a considerable cost savings just from the storage side. And then getting a little bit more into kind of like the meat of the performance metrics is we did look at like the GPU utilization between both Kubeflow and Ray. What we did notice is like, you know, GPU utilization will vary for sure during your training jobs, but like I think on average we kind of noticed like maybe about 5% more saturation on Ray compared to Kubeflow. And I should also probably just introduce the graph sides a little bit. So basically the left-hand side is average GPU utilization over like a 1-minute period. And then the bottom is just like a 20-minute period for that particular like training instance. Two is the performance metrics and I/O. So the first thing to kind of talk about here is basically the left-hand side, the left axis, which is red, is read speed. Right-hand side is write speed. So for this particular case, the reason why you'll actually see like Kubeflow kind of have like more of like a declining linear pattern here is because we're actually able to load like all the memory into data like on that particular GPU, because it's actually a smaller size for this particular experiment. In a real kind of like training environment I don't think you would expect to see a pattern exactly like this. Ray, for example, actually, the reason why we do see kind of like more of like a batch like this is actually like the Ray data API, I believe. It's more of like a batch loading for like the data that you're working with at that particular point in time. So that's why like in this case, you'll see more of kind of like at each epoch point, like why you're basically getting your read speed and your write speed to kind of like work like that. So then kind of like moving a bit more into the insights, pros and cons, and the conclusion. So for the pros of each setup, I think with Kubeflow, one thing that was really nice for us and our engineers is like it did have like built-in Docker support right off the bat. So this was great for us to basically like easily utilize like our existing like Docker images and ensure like we can basically have consistency between our like in-prem or like on-prem setup and our cloud setup, because our engineers are used to that. And then as well too, easy job launching is like as soon as you basically figured out how to set up your YAML files or you had like everything set up, is like it was really easy to basically like kick off your training jobs afterwards. With Ray, so I think like one of the things that I mentioned before is that integration with S3, and it was able to allow like our GPUs to actually achieve like higher saturation using commodity storage. So basically utilizing like cheap RAM instances, we are actually able to basically like pre-process all our data beforehand and then get like better GPU saturation afterwards. And as well too, kind of in line with that is like the streaming execution. So Ray Data's built-in like support for streaming did lower like memory and compute requirements for our large-scale training jobs. Cons of each setup, kind of like I think I mentioned before, is Kubeflow. It does have like a lot of setup complexity at the start, so it has like a decent amount of time required, and depending on your team's maturity for like machine learning infrastructures, you might have to write like more documentations and things like that. And then integration constraints is what we did notice is that like when Kubeflow, for example, maybe different portions of the Kubeflow cluster ran into issues, it would basically hinder your entire Kubeflow's cluster performance. So you might have to go into like additional pods that aren't super critical to your training job to basically like make sure or understand like why you're running into issues there. And then Ray, for example, is that while it does have a built-in integration with S3, there were challenges when optimizing I/O. So that's pretty much like why we had to utilize like Ray data. So we could kind of see this as like a bit of a pro and a con. I think it just gives you like more ability to basically like optimize your I/O because it's all within the Ray ecosystem. As well, dependency management is, I think sometimes is that in order to get like the Ray cluster to operate like the way that you want it to, is you do have to pay a lot of attention to your dependencies, but as soon as you get them right, everything will work the way that you expect it would. A couple of unexpected insights, things that we didn't kind of like realize when we were getting into this particular investigation is that we didn't expect to get better I/O using S3 than EFS, because if you actually do look at like how AWS pitches these products, is AWS will essentially pitch these products as that S3 would be like an inferior I/O system to an EFS system. So that was one of the unexpected insights that we found. Second, and I think this was kind of like good to know for now and in the future too, is that in order to optimize our training is actually like the data loader and how you feed using RAM instances to GPU instances can be super critical in order to basically like speeding up your training jobs, reducing your overall costs, and getting better GPU utilization. Three is utilizing those cheap RAM instances instead of expensive GPUs for pre-processing also can be an optimal route to take, which is one of the things that we found through this. And just in terms of acknowledgements, just like to thank Balaji and Xiao and as well the AnyScale team, because they were super helpful with this particular setup and all the collaboration work that we had. And that is also super happy to answer any of your questions now, or you're also more than welcome to find me around here or offline, and I'll be happy to answer any more questions. Thanks. Oh yeah, and there's no mic in here, so I'll get the questions and I'll repeat them back to you, and then I'll answer afterwards. Yeah.
So I do computer vision training. It's more like image classification tasks, and so I haven't really done much object detection. But is the GPU utilization around like 40-something%? Is the norm
So I don't think we've ever actually seen like GPU utilization get like close to 100. I think if you average it out over like say like a long training run, like honestly, kind of like even for an on-prem server setup, it could be like I would say 25 to 45. And anybody in here, if you have a different experience, feel free to mention as well. But I've never seen like us even on like an on-prem with like super fast like memory, like SSDs, and like using like a network file system, like being able to kind of get over like 40, 45% over like a long period of time.
Yeah, have you observed is so idle challenges sometimes is the data throughput, sometimes is the IOPS. Which one in this case? I don't know how great data uses how to shuffle it.
That's a good question. To be honest, I'm not 100% sure off the top of my head between those two, which the one with this. But if you'd like, feel free to email me or connect with me, and like I can go and double check and provide the response offline afterwards. Yes.
So you compared like Kubeflow with Ray. That was a good comparison. So you compared like the installation time of it. So Kubeflow kind of natively depends on Kubernetes, whereas Ray you have to set up a cluster, although it has compatibility with Kubernetes too. So if you think right, like if the infrastructure team needs to support it now, so they'll have to actually understand Ray, they'll have to deploy it. Whereas in terms of Kubeflow, you just need to install Kubeflow because Kubernetes is already present over there. Do you think that makes a difference?
Got it. Okay, so I'll kind of try to summarize this question. So I think the question is that basically you have Kubeflow and Ray, and correct me if I'm wrong. So you have Kubeflow and Ray, and essentially the question is that because Kubeflow is like a Kubernetes-based like deployment processes, once Kubeflow is set up, like you don't have to like basically manage any of the cluster and whatnot. Versus because Ray is essentially like you bring up the cluster at that particular point in time, is like you would have to essentially like have like more management on the cluster. Does that sound about right? Okay, so I guess to some extent it's true. It would be like this, is that like with the Kubeflow side, for example, is you'll set up your cluster at the beginning, but like after you set up your cluster is like you still do to actually kind of have to manage it to some extent. Is like in our case, for example, is that like we weren't actually training jobs on Kubeflow all the time. So actually what we would have to do before we wanted to put jobs into Kubeflow is we would actually go into like our EC2 basically, and then we would turn on our autoscaler again. So we basically bring up our like RAM-based instances for EC2 to basically like spin up our jobs. So I guess to some extent it does still actually require some like upkeep to some extent. Like it would require engineers to basically understand like how to deploy it. And then as well too is like we did actually run into like some issues too with Kubeflow in the sense of that like we would have certain pods that would go down during deployment, and then like we would have to basically go into like these sub pods and basically understand like why those are not working the way that we expected them to. Versus like with Ray, for example, is I mean based on my experience, and we were actually like utilizing like the AnyScale managed solution like while we were like investigating Ray, is it actually seemed like pretty low maintenance from like an engineer side, because like we would basically just have like our code already built, and then we would basically just submit our code, and like it would already spin up a cluster for us already. So I guess based on this comparison is that my finding would be is they both do require upkeep to some extent, but I feel is that like the Kubeflow is like you might actually, depending on, it always depends on how you're deploying these things, but the Kubeflow actually could still require like maybe a little bit more upkeep than the Ray. I guess to my user experience is that it seemed like to me Ray required a little bit less upkeep. Good question, thank you. So, sorry.
So basically, if you're using Ray, you'll have to like change your training configuration,
Yep.
your training pipeline. As you're doing Kubeflow, you don't have to change it because you just use a YAML setup for that.
Yeah, so just kind of repeating the question really quickly is that, so basically in Kubeflow is that because everything is like, in our case, we use YAML basically to set up everything. So the question is essentially is like, is there probably a lot of overhead in changing your code base, like if you're going to use Ray to start your like computer vision training jobs compared to Kubeflow? And then so for us within Kubeflow is that basically, so the requirements are get your Docker images into Elastic Container Registry, so ECR, then basically like create your YAML file with like how you need to start your job, and then 3 is basically just submit your YAML file, so that. Ray, like, I mean, as you can kind of see based off the like right-hand side here, is because all our training jobs were like natively like based out of Python, even though that we would create Docker images from those Python scripts. But I mean, even if you were just like doing experimentation, like this is like for us, so all we would have to do is basically import the TensorFlow trainer. And then basically, like, you would just create this train loop per worker. So like, instead of us maybe beforehand having like a main function, is you would just create like another function that basically would run this like per epoch type thing. So instead of maybe setting up your job for like however many epochs you need, you just like define like how that loop works like per epoch. And so I actually think it doesn't require a lot of work for us. Maybe, but it's like any tooling, right? Any tooling will have like a little bit of like learning at the beginning, but like once you get over that learning hump, like it actually is quite straightforward. And so I feel like for actually like many of the engineers on our team that are comfortable with Python, is like this would be like doable for them for sure. So maybe not too much like upkeep, yeah. And I think you had a question back there too, yeah.
Yeah. It's been my experience that EFS has an absolutely abysmal small file support. And while S3 is better, it still seems a little ridiculous. So I'm curious if you've tried any other sort of network file systems that maybe a better small file.
Yeah, totally. So just, I think everybody heard it, but basically just the, I think, summary of the question is, for EFS basically has very poor kind of small file support. S3 also isn't great. And then like, is there any other options available? So for us, what we did actually look at too, we did actually benchmark like most of the AWS storage systems for us. GP3 actually seemed to work really, really well. So if anybody is doing like any trainings, like you can look at that. I think based off our experiences, we found like for all the I/O particular throughput things that we were looking at, actually GP3 has the best. Even though I think actually I probably not 100% sure off the top of my head, but I think GP2 is actually advertised to be faster than GP3. But yeah, so for us, what we found with basically small file support is GP3 did have like very good ability. So yeah, that could be something interesting to look at in any of the distributed training cases.
Is your data stored in like NumPy formats, or how is the data generally stored? In a file?
Yep, good question. So our data, sorry, just a quick repeat, basically, it's how is the data stored and like fed into the system for us. So data store right now is like, it would basically be a like image file that either would exist like locally on like a SSD or like in the cloud on like S3, EFS, GP3 or whatnot. Basically, as it's fed into our system is we are doing like NumPy basically modifications on that particular system. So we're not actually doing any Parquet reading for like our normal like training setup that we do right now. It's all basically like NumPy modifications and operations. Yeah, good question.
For the image content, do you encoding the image back into the NumPy or still the separate file, just the file name?
Yeah. So I think the question is basically, so when we're pre-processing the images and like feeding them into our system, are we basically taking like the background too, or like adding more into the background? Sorry, maybe I'm misunderstanding the question.
I mean, for the image,
Mm-hmm.
you need to read the content during the training.
Oh, I understand.
The learning part is whether you put that content during the pre-processing into some your dataset, or you still say read the NumPy, but in the NumPy you still need the file name slash the image.
I think, yeah, so I think the question is basically, and once again, correct me if I'm wrong, is essentially is like, and I think I actually have, maybe here, this is a good slide to go on, is so basically like, are we also including some of the pre-processing steps like during the training rather than like basically all at the beginning or all at the end? So in the Ray case is like actually because we're utilizing like the cheaper RAM-based instances to basically do all the pre-processing on like our data at the beginning, is we actually find like we can do pretty much like most of those like mapping and like group bys like all within like those RAM-based instances and then just like feed it into our GPUs afterwards. So for like this case, yes. For our traditional case of like, say, if we were just like using like a commodity GPU and utilizing this, is like we would basically do that all like on each epoch. So basically at the beginning of each epoch is like we would do all that data pre-processing, and then basically like once that is ready at like the initial epoch, then like we would feed the data in once it's all been pre-processed. So in this case, you would do it basically all at the beginning on the RAM-based instances. If we're just using our GPU-based instances, like on like a local setup or whatnot, we would actually do all the pre-processing like on that GPU machine at that point in time of training. Yeah, thank you.